This afternoon I'm mostly going to be focusing on using an SLM in the context of MD-MR&D as a piece of lab equipment for modally characterizing fibers and components, with particular emphasis on maintaining high modal extinction ratios as you head to the higher order modes. An SLM is great because it allows you to generate and detect arbitrary beams in a reconfigurable way, just in software. When you build an SLM mode mux, you're not bound to any particular fiber type, number of modes, a particular mode basis. Those are all just software changes that you can make at any time. So for instance, here's my interface in the lab. You can just dial up whatever mode superposition you want, assign it to whatever fiber you like, adjust the attenuation of the modes, all software. The SLM generates arbitrary fields, not modes specifically, so you can emulate other optical components or launch conditions. So for example, here's some phase masks that could be programmed onto the SLM to emulate a 5-spot launch into a fiber. Now if you're going to be doing a lot of 5-spot launches for like a transmission experiment or something, then you're better off just doing it for real with an array of fibers. But if you're just looking to try something out quickly, then the SLM could be very productive, like in the same way that you might use a wave shaper in the lab to program an arbitrary optical filter rather than ordering a custom filter. You can try a lot out very quickly. So here it is adjusting the mode field diameter of the spots, adjusting their spacing, rotating the pattern, adjusting the relative amplitude and phase of the spots. So you can adjust the phase tilt across the whole 5-spot pattern as if you're coming in at an angle. This is the basic setup for a phase plate-based mode conversion. When used as a multiplexer, the SMF illuminates the phase mask, which contains some 2D spatial phase distribution, which converts the beam into an approximation of the desired mode. And the same principle holds in the reverse direction when operating as a demultiplexer. Mode comes in, phase front gets flattened out and converted into something that looks like a Gaussian as it's coupled into the single mode fiber. This is the schematic of the system I use for mode multiplexing. It consists of an input array of single mode fibers. Each of these fibers can be used as a separate channel, or if you're just modally characterizing something, you might just use one of them. The beam goes through a PBS so that each polarization can be addressed independently. Each beam then reflects off the SLM. I usually draw it unfolded in 2D for clarity, as if the system was transmissive, but in reality the incoming and outgoing optics are actually folded on top of one another, like so. Each polarization reflects off the SLM before being recombined by the outgoing polarization optics and coupled into the fiber under test, which is a multi-mode fiber. Ignoring any mode conversion for a second, which input fiber is coupled to the output multi-mode fiber is defined by the blazed grading pattern programmed onto the surface of the SLM. It's also possible to superimpose multiple gratings together to couple light from multiple inputs to the same output, but when multiple masks are superimposed, a beam splitter-like loss is incurred. So it's like a beam splitter, which you can add or remove in software and don't have to worry about aligning, but you still pay the loss. And in that way, you can modally multiplex multiple channels. So do a simple single channel example here. Light from the single mode fiber comes into the SLM with some particular polarization. It reflects off a grating with a fork dislocation in it, converting it to an OAM mode, which is then coupled into the fiber under test. At the other end, due to mode mixing, modal birefringence, it shows up as some random superposition of LP11 modes. And if you know what that superposition is, you can program the receiver SLM to convert those modes back to Gaussians and into the assigned output fiber. It's like kind of optical MIMO. If you were doing a transmission experiment, you could have multiple input and multiple output fibers going at the same time with superimposed masks at the transmitter and receiver. For characterization purposes, You can use the system to measure the propagation matrix of the fiber in the modal transfer matrix, and the matrix which relates every modal input to its corresponding output. Here's an example of what a 3-mode fiber, or like a 6-mode fiber, 3 in each polarization. To measure the amplitude of the matrix, you transmit each mode one at a time from one end, and then display masks for each of the basis modes one at a time at the receiver to measure the power arriving in each mode. You could easily measure both receive polarizations in parallel to speed up the process, or if you're willing to take the beam splitter loss hit, you can measure some or all of the received basis modes in parallel using different output fibers. This is just a 2-meter piece of few-mode fiber patch cable, and you can see the 2 orthogonally polarized fundamental modes mostly stick together, and the 4 LP11 modes also mostly mixed together. However, that's only partial information about propagation matrix. If you're also interested in the phase, that's something the SLM can also measure. For example, if we're ignoring polarization for a second, here's the mode arriving at the receiver as some random superposition of LP12 and LP31 modes. In the middle will be the phase masks displayed on the SLM in the image plane, and on the right is the Fourier plane representing the plane of the output single mode fibers, which are attached to a power meter. First, the SLM displays masks for each of the basis modes one at a time and measures the power coupled into the output fiber as described in the previous slide. Now the amplitude of each mode is known. Then it adds together the masks for each of the basis modes one at a time with various relative phases to work out the relative phases between the modes. When the phase is conjugated with the beam and all the amplitude and phase values are correct, then you get a bright correlation spot, like on the right there, and the coupling to the output is maximized. Here's an example of how that plays out on the SLM in practice from the lab. It quickly flashes each of the basis modes and measures the power, then sweeps the relative phases between the modes as it adds the masks together, and you can see the power varying on the power meter. You get all the modal coefficients up here. Here's that propagation matrix from before, now with the phase information filled in as well for that short piece of patch. And if you multiply it by its conjugate transpose, you can see that you get the identity matrix, verifying that it's unity. When working with few-mode fiber, the faceplate used typically just takes the form of the phase of the mode itself. The resulting beam isn't exactly correct, but if the fiber doesn't support any modes of similar symmetry, that's the best way to go. For example, here's the mode transfer matrix using the phase-only approximation for a 3-mode fiber like before. It contains LP01 and LP11 modes. They've got completely different symmetries, and when you normalize out the mode conversion loss of the higher order modes, you're left with the identity matrix. Now for a 6-mode fiber, most modes are still good, except there's crosstalk now between the LP01 and the LP02 modes. And you could get rid of that actually if you adjusted the focal length ratios. But if you go to 10 modes, you can see now you've got crosstalk between the LP11 and the LP12, and so forth. So there's a 55-mode fiber, and you can see the crosstalk between all the modes of similar symmetries, with the higher order modes being the most sensitive, as you might expect. When you make these simplified masks, information about the phase of the mode was kept to make the mask, and the amplitude information was simply discarded. So in order to get that information back, you need to generate phase masks which take the amplitude distribution of the mode into account. I talked about that last year, so I'm not going to go into details, but you can look up my talk from last year on YouTube. My point is, when you start characterizing systems or components that support more than about 6 modes, having more accurate masks becomes important. And when you do that, theoretically at least, you can virtually eliminate crosstalk between the modes. On the left, it can be seen how in the phase-only approximation, as you add more modes of similar symmetry, the worst case crosstalk continually degrades, or represented a different way, the mode-dependent loss, the orthogonality between the modes, gets worse and worse, whilst the optimized mask case grows very slowly. When performing mode conversion, you also have to match the numerical aperture of the single mode fiber to the mode of the multi-mode fiber you're trying to excite if you want to maximize efficiency. For few mode fiber, all the modes have almost the same NA, which in turn is almost the same as the NA of the single mode fiber. But for multi-mode fiber, there's a large spread in numerical apertures for all the different modes. For example, here's the optimal focal length ratios matching an SMF to each mode of a 50 micron core graded index multi-mode fiber. You've got the highest order mode with an optimal magnification of 2, which is basically the ratio of the NA of the SMF, about 0.1, to the NA of the MMF, about 0.2, down to the fundamental mode of the MMF, which actually needs to be scaled to 75% to match the SMF. For absolute maximum efficiency, you'd use a different lens for every mode, but that's not really practical if you want fixed optics. You just want to use different SLM patterns for each mode. When you decide upon a focal length ratio, when you build a system, you're deciding what band of modes you can excite efficiently and which you cannot. I generally configure mine about here. It's sort of like a good compromise. Here I've calculated some optimized masks for different focal length ratios. The masks can maintain the orthogonality between the modes even if you've used a suboptimal focal length ratio indicated in the red, but you pay a loss for violating the NA. Match it perfectly for the fundamental and you'll have high lower order mode efficiency, but you'll be unable to excite the higher order modes using the same optics. Match it to the higher order modes and you'll lose lower order mode efficiency. You can also see that if the NA mismatch gets too severe, you'll eventually start to lose orthogonality between the modes as well. Another convenient aspect of an SLM is that it allows you to perform a lot of the fine alignment of the system in software without moving parts. So here's a system attempting to find a particular output fiber by adjusting the phase tilt of a blade's grating for each polarization. And you can see that the two polarizations aren't exactly the same, and that's because my mirrors and beam splitters aren't exactly at right angles to one another. They calibrate that out. So that tilt alignment that's doing there is as if you were moving your input or output fiber in the X and Y plane. You can also find the center of the beam as if you're moving the SLM itself in X and Y. You don't actually have to touch anything when you're doing the fine alignment. You don't have to worry about, if you adjust your knobs, that you won't be able to get it back to the same position it was before. With an SLM alignment, it's all software, so if you stuff it up, you just Control Z without having to move anything. And because of all that, you can make the system quite compact. This is what it looks like in the lab. So you've got a transmitter there, a receiver there. It's got an Australian dollar coin on there, which is about the size of a quarter. But even assuming you have perfect masks and you aligned it perfectly, in practice, optical aberrations can decrease the accuracy of your modal measurements. Generally, you work on the assumption that the wavefront from your single mode fiber is flat, but the optical elements in your system, such as the lenses and the SLM itself, can distort that wavefront. So, for example, here's an interferogram of the surface of an SLM that was measured by Christoph Bay at the University of Cambridge, and the fringes here indicate that it isn't optically flat. It's kind of bulged in the middle. However, if you know that profile, you can apply the conjugate phase to all the masks you program onto the SLM and cancel that out. I'm going to talk a bit about aberrations here and their effects on your modal excitations / detection. On the left, here we have the distorted wavefront. In the middle, we have the mode transfer matrix due to that aberration. And on the right, we have the effect that aberration would have on your fundamental mode as an example. Ideally, if you ask your system to excite a particular mode, it will excite only that mode. But aberrations cause the modes to become coupled together. So first of all, there's tilt. And tilt's not really an aberration per se. It just means that you're not aiming at the center of the fiber. And if you just move the fiber in X and Y, you should fix that. So basically, if you've got a tilt problem, your optical components aren't the problem, you're the problem. The higher order modes are most sensitive to alignment, as you'd probably expect. And as you get off center, you start exciting LP11s instead of the fundamental, followed by LP02, LP21, and so forth. Defocus isn't really an aberration either. If you move your fiber in the Z-axis in and out, that should go away as well. But we can see that if you are out of focus, modes of similar symmetry start to get coupled together. LP11 starts to excite LP02, LP03, etc. Astigmatism means your focal length along the X-axis isn't the same as along the Y-axis, as if your lens is a bit cylindrical. Maybe your SLM is rectangular and bulges sort of more along one axis than it does along the other. You can see the different aberrations have phase fronts that kind of look a bit like the modes themselves. Like you can see, for example, here astigmatism looks a lot like an LP21 mode, and that's why LP01 becomes coupled to the LP21 in its presence. Coma is the kind of thing you'd encounter if you're working off axis. Maybe you're not going through the center of the lens or something. All kinds of modes of coming out of the woodwork there. But if you extend your alignment process beyond just trying to find the XY position of the fiber, but instead use the SLM as like a wavefront sensor, we can calibrate all those aberrations out as well, measured in situ. Here's an example before aberration correction. On the left is the wavefront correction, nothing in this case. And here is the coupling between input and output as a function of X and Y tilt with only SMS plugged into the system. So basically I'm using the SLM and a power meter like a kind of camera. I can scan the spot across the output single mode fiber by adjusting the phase tilt on the SLM and measure the power. This is the coupling distribution when the system was first assembled. We've got a loss of about 4.82 dB. I mean, it's dB scale, so it's probably not as bad as it looks. But then you apply the correction mask, and the loss drops to 3.51 dB. And there's still like a bit of a pedestal there, but it looks a lot better. And here's another example. The initial state is much better, 3.8 dB, and the wavefront requires less correction, and the result is also better, 3.38 dB of loss, and it looks quite Gaussian even down to -40. This is from a different SLM than the previous two, but if you scan the correlation masks for each of the other modes across the core, then you can also observe their cross-correlation distributions. Now there are only single mode fibers plugged into the system, so the only mode with a correlation in the center should be the fundamental mode. Any power that shows up there is due to aberrations. This is probably maybe a bit of coma, distorting our LP11, some spherical, distorting the LP02, and some astigmatism that's more in the direction of LP21A than LP21B. Here's an example of how that plays out for a mode transfer matrix measurement. With the correction off, there's a lot of mode coupling, particularly between modes of similar symmetries, between like mode groups 3 and 5, 7 and 9, etc. But with the mask turn on, you can get something that looks much more like the skewed identity, which you would expect. Now this system was probably a bit out of focus at the time as well, so you probably could have got a bit better just by moving the lens a bit, but the point is that the difference between those two is just a software change. So with all that in place, I think it's time to measure a big matrix. Here's an example of the full 110 by 110 propagation matrix for a standard piece of 50 micron core multi-mode fiber patch cable. I'll be talking about this more at ECOC, but that propagation matrix maps any given input to its corresponding output, and naturally any particular output with the corresponding input. So rather than launching in a pure mode at one end and having a mixed mode arrive at the receiver, you can launch in a mixed input to get the desired mode at the output. And here's an example of that for a vertically polarized LP05 mode. From the measured matrix, the required input should look something like this. So a pattern required to generate that modal distribution is displayed on the SLM, and the output on the right there is observed on a camera at the output. And here's some examples for some other modes. I've got an OAM spin 8 coming out horizontally polarized. One of the LP81 modes is more lossy than the other, which makes it kind of splotchy. If you want to get fancy, you can make two different modes come out of two different ports of the beam splitter, or the polarizing beam splitter. So here's an LP04 coming out one port of the beam splitter, LP42 coming out the other. And for good measure, I've got an example of a sort of lower-ish order mode coming out as well, LP22. So thank you, I'll leave it there.